let's look at an introduction to inference procedures for two proportions. In this video, we will discuss confidence intervals and hypothesis tests for the difference in population proportions. The methods used in this video are large sample methods based on the normal approximation. Let's look at an example. A study of births in Liverpool investigated a possible association between parental smoking during pregnancy and the sex of the baby. In a sample of 5,045 babies born to non-smoking parents, 2,685 were male. P1 hat, the sample proportion of males for non-smoking parents, is 2,685 over 5,045, or about 0.53. In a sample of 363 babies born to heavy smoking parents, 158 were male. P2 hat, the sample proportion of males for heavy smoking parents, is 158 over 363, or about 0.43. The difference in sample proportions, P1 hat minus P2 hat, estimates the difference in population proportions, P1 minus P2. P1 is a parameter representing the true proportion of male births for non-smoking parents, and P2 is a parameter representing the true proportion of male births for heavy smoking parents. Here are two very common points of interest in scenarios like this. We often wish to construct a confidence interval for the difference in population proportions. And we often want to test the null hypothesis that the difference in population proportions is zero, or, equivalently, that the population proportions are equal. In the male birth rate example, this null hypothesis would mean that there is no association between parental smoking and male birth rate, or that non-smoking parents and heavy smoking parents have the same proportion of male births. And we'd like to see if there is strong evidence against that. Is parental smoking related to the proportion of male births? The difference in sample proportions estimates the difference in population proportions, and to construct the appropriate inference procedures, we need to know the characteristics of the sampling distribution of the difference in sample proportions. So let's look at that. I take a closer look at the sampling distribution of the difference in sample proportions in another video. These are the characteristics that we need for now. The sampling distribution of P1 hat minus P2 hat has a mean of P1 minus P2. The difference in the sample proportions is an unbiased estimator of the difference in population proportions. The standard deviation of the sampling distribution of the difference in sample proportions is equal to this quantity. And the difference in sample proportions is approximately normal if the sample sizes are large. In order for the inference procedures we are about to discuss to be reasonable, the following assumptions must hold. We need independent, simple random samples from the populations of interest, or we might use these methods to analyze the results of a randomized experiment. And the sample sizes must be large enough for the normal approximation to be reasonable. These are large sample methods, and they are not appropriate for very small sample sizes. I'll give some details about how large a sample size is required in the text and the video description. If those assumptions hold, a 1 minus alpha times 100% confidence interval for P1 minus P2 is given by this formula. We start with our best estimate of P1 minus P2, which is P1 hat minus P2 hat, and we add and subtract this margin of error. The margin of error is made up of the z sub alpha over 2 value, which we've discussed in great detail previously, times the standard error of our estimator, P1 hat minus P2 hat. What is the appropriate standard error? Recall that the standard deviation of the difference in sample proportions is equal to this quantity. So ideally, we'd love to use this quantity in the confidence interval formula. But in practice, we can't calculate this because we don't know the value of P1 or P2. So we do the next best thing and we estimate P1 with P1 hat, we estimate P2 with P2 hat, and we call that the standard error of the difference in sample proportions. That's the standard error that we use in our confidence interval formula. We often wish to test the null hypothesis that the population proportions are equal. We may wish to test hypotheses like the unemployment rate is the same for men and women, or that two surgery methods have the same proportion of successful outcomes. The alternative hypothesis will be one of these three options. As per usual, the appropriate choice of alternative hypothesis will depend on the problem at hand, and we will choose the two-sided alternative hypothesis unless we have a strong reason to be interested in only one side. To test that null hypothesis, we will use this Z statistic. We take the difference in the sample proportions and divide by the standard error of the difference in the sample proportions. I've put a subscript of 0 here because this standard error for the hypothesis test differs from the one we use for confidence intervals. Recall that the standard deviation of the difference in sample proportions is equal to this quantity. But we can't use this in the formula because we don't know the values of P1 and P2. We could replace them with the estimated values P1 hat and P2 hat, like we did with the standard error in a confidence interval, and that wouldn't be silly, but we do something a little different in hypothesis testing. Recall that in hypothesis testing, we construct a test statistic that has a known distribution, assuming the null hypothesis is true. Here, the null hypothesis is that the population proportions are equal, and if this null hypothesis is in fact true, then the sample proportions P1 hat and P2 hat estimate the same quantity, the common population proportion. So we pool the two sample proportions together. The appropriate standard error is this quantity, where P hat is the pooled sample proportion, which is the proportion if we treated all individuals from both groups as if they were in one big group. X1 plus X2 is the number of individuals with the characteristic of interest, and N1 plus N2 is the total number of individuals in both groups combined. If the null hypothesis is true, this Z statistic will have, approximately, the standard normal distribution. So we will get our p-value in the usual way, by finding the appropriate area under the standard normal curve. Let's take a quick look at that. Suppose we have this alternative hypothesis, that P1 is less than P2. I've drawn in the standard normal distribution, which is the distribution of the Z test statistic if the null hypothesis is true. Suppose, for example, we get our samples, carry out the calculations, and get a Z statistic of minus 1.20. For this alternative, the p-value is the probability, under the null hypothesis, of getting this value or something even farther to the left. And that is simply this area, the area to the left of minus 1.20 under the standard normal curve, which we'll find with software or a standard normal table. Suppose instead we had this alternative hypothesis, that P1 is greater than P2. Then the p-value is the probability, under the null hypothesis, of getting the observed value of the test statistic or something even greater. Suppose again that we draw our samples and find that the Z statistic equals minus 1.20. The p-value is the area to the right of minus 1.20 under the standard normal curve. Suppose instead we had a two-sided alternative hypothesis. Then the p-value is the probability, under the null hypothesis, of getting the observed value of the test statistic or something even more extreme, something farther out in the tails. Suppose again that the value of the Z test statistic is minus 1.20. The p-value is the probability, under the null hypothesis, of getting minus 1.20 or something even more extreme. Part of that probability is this area to the left of minus 1.20. But we would have thought it exactly the same amount of evidence against the null hypothesis had we gotten a Z value of positive 1.20. So the p-value is the sum of these two areas. Another way to think of it is that the p-value is double the area in the tail beyond the observed value of the test statistic. Here, the p-value is double the area to the left of minus 1.20. Once we get the p-value, we draw a conclusion in the usual ways. A very small p-value gives very strong evidence against the null hypothesis and in favor of the alternative hypothesis. And if we are carrying out a test with a set significance level alpha, we reject the null hypothesis in favor of the alternative hypothesis, or say that the evidence against the null hypothesis is statistically significant if the p-value is less than or equal to the alpha value that we are using. I worked through an example with detailed calculations in another video, but here let's return to the male birth rate example from the start of this video and take a quick look at the results of the calculations. The sample proportion of male births to non-smoking parents was approximately 0.53, and the sample proportion of male births to heavy smoking parents was approximately 0.43. In studies like this, we often wish to test the null hypothesis that the population proportions are equal. We typically use a two-sided alternative hypothesis, as we are usually interested in a difference in either direction. This null hypothesis means that the true proportion of male births is the same for non-smoking parents and heavy smoking parents. The alternative hypothesis is that there is a difference in the true proportions. You can verify for yourself that if we use the methods I just discussed, we get a z-value of approximately 3.57, with a corresponding two-sided p-value of 0.00035. This is a very small p-value, implying very strong evidence against the null hypothesis and in favor of the alternative hypothesis. This p-value is small enough that the evidence against the null hypothesis would be considered statistically significant at any of the usual significance levels, such as 0.05 or 0.01 or even 0.001. So there is very strong evidence that the true proportion of male births differs between non-smoking parents and heavy smoking parents. But a conclusion that there is a difference on its own is not very informative. We are almost always interested in the nature of that difference. Here, note that the sample proportion of male births to non-smoking parents is greater than that of heavy smoking parents. So this study gives strong evidence that non-smoking parents have a greater proportion of male births than heavy smoking parents. If we calculated a 95% confidence interval for the difference in true proportions of male births, we'd see that it works out to 0.044 to 0.150. This entire interval lies to the right of 0. So based on the interval, it looks like P1, the true proportion for non-smoking parents, is greater than P2, the true proportion for heavy smoking parents. This shouldn't be too surprising, given the results of the hypothesis test. And, to my eye at least, that looks like a surprisingly large difference in the male birth rate. This was an observational study and not an experiment, so it does not give evidence of a causal effect. We are not saying that parental smoking causes a lower male birth rate. We are simply saying that there is strong evidence of a relationship between parental smoking during pregnancy and the proportion of male births. There are many lurking variables that could possibly be the cause of this observed relationship. And note that this study was based on data from hospitals in Liverpool, England. If we change the location or change the time frame of the study, we may very well end up seeing a very different relationship. There are alternative approaches to the methods used in this video, including adjustments that improve the normal approximation, other statistical tests that are sometimes used in these scenarios, and the difference in proportions might not be the most meaningful measure. Sometimes, especially for small proportions, the relative risk, which is the ratio of proportions, is a more meaningful quantity. With the relative risk, we can say things like, individuals with a certain risk factor are 3 times more likely to develop lung cancer. Quite often, this is a more meaningful measure than the difference in proportions. In another video, I work through a complete example of the inference procedures we discussed in this video.